Colligative properties of strong electrolyte solutions. When you have an electrolyte as your solute, the colligative properties are intensified. Because if you have 1 mole of sugar, you have 1 mole of particles. If you have 1 mole of sodium chloride, you have 2 moles of particles, right? 1 mole of sodium ions and 1 mole of chloride ions, because strong electrolytes separate into ions. So we have to factor that in, and we use the Van 't Hoff factor to do that. It's the ratio of moles of particles to the moles of formula units dissolved. So the Van 't Hoff factor will depend on the formula of the compound. So I is the moles of particles divided by the moles of formula units. The actual Van 't Hoff factors are not exactly the same as what we expect them to be. Sometimes they're pretty close, sometimes they're way off, and the reason is that some ions pair up even though they're in solution. So this is what ion pairing looks like. Here we've got a chloride ion surrounded by the water molecules, and we've got a sodium ion also surrounded by water molecules, but they're still somewhat attracted to each other, and so they kind of pair up, and they hang out together, and so they act kind of as 1 particle instead of 2 particles. Here we have a table listing the expected Van 't Hoff factors and the measured Van 't Hoff factors. For a non-electrolyte, those factors are 1, and we just can ignore that. For something like sodium chloride, 1 sodium ion, 1 chloride ion in a formula unit. There's 2 ions per formula unit. So that's the expected. The measured is pretty close, it's 1.9. So that tells us that sodium chloride doesn't do a lot of ion pairing. Magnesium sulfate, we expect a Van 't Hoff factor of 2. Again, because we've got a magnesium ion and a sulfate ion, 2 ions. But the actual Van 't Hoff factor is 1.3 because of ion pairing. The ion pairing is going to make the Van 't Hoff factor be smaller. It'll never be larger. Any questions? You do not memorize measured Van 't Hoff factors. You should be able to figure out the expected ones by looking at the chemical formula. Just the number of ions that form. So to use this Van 't Hoff factor in these equations for the colligative properties, it's just multiplied. So the freezing point depression is going to be the Van 't Hoff factor times the molality times the freezing point constant. So let's do an example of this. Calculate the freezing point of an aqueous 0.10 molal iron 3 chloride solution using a Van 't Hoff factor of 3.2. So here they're giving us the actual Van 't Hoff factor. The expected one, what would the expected one for this compound be? How many ions are in 1 unit of FeCl3? 4 ions. We expect it to be 4, it's actually 3.2. So the freezing point, we use the freezing point depression equation, so delta TF. Now we're going to use the Van 't Hoff factor and the molality and the freezing point depression constant for water. So I is given, it's 3.2. The molality was also given, 0.10 molal. Such a stupid unit. And then we need Kf. And because I've been lecturing on this, I happen to remember that one. You would look that up in the table. This is the freezing point depression constant for water. It's for the solvent. And then you dig out your calculator. Uh, 3.2 times 0.1 times 1.86. So 0.5952 degrees Celsius. That would have 2 sig figs. Is that the freezing point? No. That's the change in the freezing point. Okay? So we have to take the change in the freezing point and combine it with the actual freezing point of the solvent. What's the freezing point of water? 0 degrees.
32 degrees Fahrenheit.
It's 32 degrees Fahrenheit or 0 degrees Celsius. So the freezing point depression, the freezing point goes down when you add a solute. And so we have to subtract that number. And so we're going to get minus 0. I'm going to round it to 2 sig figs now. Minus 0.60 degrees Celsius. Any questions? Yeah.
Where did you get the 1.86 degrees Celsius?
I pulled it out of my head, but it's in a table. Right there. So
We can just look it up.
you would just look it up, or it would be given to you. And here's the freezing point. I don't expect you to know freezing points or boiling points for anything other than water, but you should know the freezing point and boiling point for water. Okay. The boiling point elevation constant is different than the freezing point depression constant. So you would just look that up. Any other questions? Okay. Strong electrolytes also have a larger effect on vapor pressure lowering. So when we calculate vapor pressure from strong electrolyte solutions, we have to account for the dissociation when we're calculating the mole fractions. So that's what I was talking about up here on the board. It's the mole fraction times the vapor pressure of the pure solvent. When you calculate the mole fraction, you have to account for the numbers of particles. We're not going to apply Van Hoff factors. We're not going to worry about ion pairing. We're just going to look at the chemical formulas. Okay, so a solution contains 0.115 moles water and an unknown number of moles of sodium chloride. The vapor pressure of the solution is at 30 degrees is 25.7 torr. The vapor pressure of pure water at that same temperature is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. So this is a nice Chem 1A problem. It's not just plug into the formula like we did in the last example. Well, what do we know here? We can write down what's given. So we've got a number of moles of water. So we could call that NH2O. It's the number of moles of water. That's 0.115 moles. We know the vapor pressure of the solution. So P solution is 25.7 torr. And we know the vapor pressure of pure water, and that's 31.8 torr. And we want to know the number of moles of sodium chloride. So look, we're looking for moles of sodium chloride. So we look at these pieces, and it's a little bit like assembling. It's like assembling a Lego set without the instructions. Is what it's like. It's like somehow these put together. Well, P solution and P for the pure solvent. The vapor pressure of the solution equals the mole fraction of the water times the vapor pressure of the pure water. Everybody okay with that? If it's pure water, the mole fraction of water would be 1. And then the pressure of this thing would equal the pressure of pure water. The less water is present, the more solute is present, the lower the vapor pressure from the water is. Well, we know the pressure of the solution and the pressure of the water. We can calculate the mole fraction of water. That might be a good thing to do. So the mole fraction of water is going to be the vapor pressure of the solution divided by the vapor pressure of pure water. So 25.7 torr divided by 31.8 torr. And the torrs cancel out. So we get 0.80818 with 3 sig figs. Well, that's nice. We know how many moles of water there are. We want to know how many moles of sodium chloride. We know what the total mole fraction for the water is. So the mole fraction of water equals what in terms of just variables?
Moles.
Moles of water divided by moles of total solution, right? So moles of water plus moles of solute particles. Sodium chloride is a strong electrolyte, right? So this is moles of ions down here. We'll just call it that. The moles of ions, not the same as moles of sodium chloride. We won't worry about that yet. So we know one of these, 0.115 moles, and this is 0.115 moles, plus moles of ions. So 0.80818 equals this mess. We have to do some algebra. So I'm going to erase this thing. So I'm going to cross multiply 0.80818 times 0.115 moles plus number of moles of ions is going to equal 0.115 moles. Anybody have a problem with that? So then we have to distribute the 0.80818 through this, and times 0.115. Yes? Could you say it a little louder?
What would it be the moles of ions instead of this?
Okay, that's a good question. Why did I write moles of ions down here instead of moles of sodium chloride? Because when the sodium chloride makes a solution, the ions separate. Vapor pressure lowering is a colligative property, meaning it depends on the number of particles. So we have sodium ions and we have chloride ions, and so we're just going to avoid thinking about the relationship between moles of ions and moles of sodium chloride until later. That's an excellent question. This is why when you have an algebra class, they give you whole numbers instead of these messy fractions, because it gets just really tedious to do algebra with all these messy numbers. So we need to take 0.115 and subtract this. So our next step, we're going to end up with 0.80818. And ions is equal to 0.022060 moles. And then we divide both sides by 0.80818. And we get moles of ions. Actually, it over here. Moles of ions equals 0.02730 moles. Did I do that right? Anybody following? Now we need to think about the relationship between the ions and the sodium chloride. Let's make a little space up here. So if I have 1 mole of sodium chloride, and that dissolves into ions, how many moles of ions do I have? 2 moles of ions. So 1 mole of sodium chloride equals 2 moles of ions. I can use this relationship to convert moles of ions into moles of sodium chloride. You don't have to do it this way, but if your brain is doing somersaults, this is how you can prove to yourself whether you're supposed to multiply by 2 or divide by 2. I mean, it's a 50-50 chance, right? So I want moles of ions on the bottom. I want moles of NaCl on top. And the units tell me, oh, I'm supposed to divide by 2. 1 mole of sodium chloride for 2 moles of ions. We divide by 2. We come up with 0.0136 moles of sodium chloride. Now, significant figures with a calculation like this are messy and ugly, and I don't feel like dealing with them. And honestly, what's more important than getting your sig figs exactly correct is having a clue about how many you should have. This, I'm guessing, is maybe a little bit too many, but it's not crazy. And it's not rounding off to 0 or something equally crazy. Any questions? Colligative properties are very important in medicine. So you go in for a procedure, and one of the first things they do is they hook you up to an IV, right? And they hang this bag of stuff, and it's going like right into your bloodstream. It's very important that the solution they're putting into your blood has the same osmotic pressure as your blood. It has the same well, I don't know where I'm going with that sentence. Anyway, here are some micrographs of red blood cells. This is what normal red blood cells look like. Kind of look like, I don't know, funky hats or something. They're nice and round, but then they've got this indentation here. This is red blood cells in an isoosmotic or an isotonic solution, where the solution has the same number of particles per liter as the red blood cells fluid on the inside does, because the red blood cells have semi-permeable membranes, and so osmosis will happen through those membranes. We don't want water flowing in or out of the red blood cells. So if we have a hyperosmotic solution or hypertonic, the red blood cells will shrivel up. This is called crenation. And this is caused by the solution outside being more concentrated. And so the water that's present inside the red blood cells moves out in an attempt, in my crazy chemistry land, in an attempt to dilute that outside solution. So the water flows out and the red blood cells shrivel up. That's not good for you. If you have a hypoosmotic or a hypotonic solution where the concentration is less on the outside, then the water will flow into the red blood cells and cause them to swell. That's not great either. If that continues, they'll actually rupture. So these sorts of things are important. Any questions about that? When they give you an IV, they use isotonic saline. It's 0.9 grams sodium chloride per 100 milliliters of solution, or a 0.9% mass to volume. So we've talked about mass percent, we've talked about volume percent. This is a mass of solute per volume of solution. Did it just click for you? The reason they use mass to volume is these are all solutions, right? Solutions are measured in volume. It's the easiest. And there are small quantities of solute, maybe some sort of a medication or something, and that's usually measured in milligrams. And so they measure the solute in mass, the solution in volume. So 0.9% sodium chloride solution is not going to cause your blood cells to either shrivel or explode, which is a good thing.